Welcome to the presentation on inductors. Some of the objectives are to become familiar with the basic construction of an inductor, the factors that affect the strength of the magnetic field established by the element, and how to read the nameplate data. Also to be able to determine the transient response of an inductive network and plot the resulting voltages and currents, and also to understand the impact of combining inductors in series or in parallel. The three basic components appear in the majority of electronic systems that are in use today. They are the resistor, the capacitor, and the inductor. In many ways, the inductor is the dual of the capacitor. That is, the voltage of one is applicable to the current of the other and vice versa. In other words, we can also view the inductor as the complement of the capacitor. Like the capacitor, the inductor exhibits its true characteristics only when a change in voltage or current is made in the network. Inductors store energy in the form of an electromagnetic field. Here we have diagrams of how the lines of flux emanate from permanent magnets. Please note that the lines of flux emanate from the North Pole and then extend towards the South Pole. In the bottom right, we can see that a piece of soft iron has the ability to channel the lines of flux through it and alter the position of the lines of flux. Notice in the diagram in the top right, we can see that in the center we have north and south poles, so there's an attraction, and in contrast to the bottom left diagram, in the center there's a repulsion that occurs between the lines of flux between the two north poles. In every instance, however, there is still the flow from the North Pole to the South Pole of the flux lines. The understanding of how soft iron can channel lines of flux can be used to protect sensitive equipment, such as shown in this diagram. Therefore, the sensitive piece of equipment is surrounded by soft iron, and therefore any magnetic field or the lines of flux of that magnetic field are channeled to go around the sensitive instrument and not affect it. Wires that carry current also have a magnetic field. Here we have illustrations of a straight wire, such as the top left. We can see that the magnetic flux lines are indicated. We can also see how the magnetic flux lines are traveling if a coil is made in a wire. Then towards the bottom left, we see many turns on that coil. And we can see that overall there is an establishment of a north and south pole. And then the lines of flux can be increased by concentrating the magnetic field on a piece of steel, again establishing a north and south pole with the lines of flux traveling from the North Pole to the South Pole. An electromagnet is made in this exact same way, where a piece of steel or soft iron is then surrounded by a coil of wire and then current passes through it. The steel concentrates the lines of flux and makes a very strong magnet. But since it is dependent on the current flowing through it, therefore is an electromagnet. And when the current stops flowing, the magnetic field disappears. The direction of the magnetic flux lines can be found by simply placing the thumb of the right hand in the direction of conventional current flow and noting the direction of the fingers. Notice that the thumb points towards the North Pole, and the lines of flux are traveling out of the North Pole and go around and come back in at the South Pole. Magnetic flux is measured in Webers. The applied symbol is the letter phi. The number of flux lines per unit area is called flux density. It is denoted by the capital letter B and is measured in Teslas. 1 Tesla is equal to 1 Weber per meter squared. The flux density of an electromagnet is directly related to the number of turns of and current through the coil. The product of the two is called magnetomotive force and is measured in ampere turns, as defined by magnetomotive force is equal to N times I. Now N is the number of turns and I is the current. A magnetic field can be measured by using a milligauss meter, as shown here. Here are but just a few magnetic field applications: motors, transformers, loudspeakers, analog meter movements, relays, and even MRI machines. All these apply magnetic field principles. Well, what is inductance? Well, inductance is really the strength of the magnetic field around a coil due to applied current. That really is what inductance is. But what is an inductor? An inductor is simply a coil of wire with or without a core through which current is sent. The current through the wire establishes a magnetic field through and around the unit. Now, the higher the inductance level, the greater is the strength of the magnetic field. Again, an inductor stores energy, and it stores energy as an electromagnetic field. So therefore, if the magnetic field is stronger, it's storing more energy. The level of inductance is dependent on the area within the coil, that is the cross-sectional area, the length of the unit, and the permeability of the core material. Permeability is the ease in which magnetic flux lines are established in a material. For an inductor, it would be the core material. Now, in some instances, an inductor could have an air core. In other instances, it might have an iron core or perhaps a ferrite core. Depending on the application in which this inductor is to be used will depend as to what the core is. Inductance is also sensitive to the number of turns of wire in the coil as dictated by the following equation, where inductance is equal to the permeability times the number of turns squared times the cross-sectional area in meters squared all over the length of the coil, which is in meters. And the unit for inductance is henries. Here we have some of the most commonly used inductor schematic symbols. We have the air core, iron core, ferrite core, variable ferrite core, and the tapped inductor symbol. Here are a few fixed inductors. On the top here we have what we call toroids, and these are a ferrite core. And depending as to what the application is, depending as to what the frequency of operation is, how much energy the inductor is supposed to store, will depend on its size and the amount of turns that the wire has and the gauge of the wire itself. Here on the bottom of the page, we have some smaller sizes, and these are basically encased in resin or a plastic core, but they are smaller, and these are in an axial type of a package. Fixed inductors can come in, again, all sizes, many different types of packages. It really depends on the application, and here are just a few of them. We have air core, which is the top left, but then we have the toroid coil, we have the hash choke coil, have a delay line coil, common mode choke coil, have RF chokes, we have molded coils, and of course we have the surface mount inductors as well. So there's many different types of packages, really dependent on as to where it's going to be used and what the application is. Variable inductors are ones whose inductance can be varied, can be changed. And usually it's going to be through some sort of a screw adjusted type of a core. And as it states here, in each case the inductance is changed by turning the slot at the end of the core to move it in and out of the unit. So by moving the core in and out of the coil itself, the inductance is varied. The farther in the core, then the more ferromagnetic material is part of the magnetic circuit. Therefore, the higher is the magnetic strength, and therefore it stores more energy. Now, when we're talking about inductance and we're talking about the ideal inductor, then pretty much all we think about is just the inductance part. But unfortunately, inductors are not ideal, and so therefore they have other factors that are involved. And one of them is the resistance of the wire itself. The other one is because of the turns that are in the coil. One turn to the next coil, it's going to introduce capacitance. So that's going to be another aspect. Now, on the left here, you have the complete equivalent model for an inductor. And notice that it has an R part, has a C part as well, and on top of the inductance itself. And then from the practical equivalent model for an inductor, we see that it's going to be a resistance in series with an inductor, and the resistance comes from the wire itself. Please note that there are inductors that look like resistors, and they'll have color codes associated with them. Here's just an example of a color code table, and again, this is just for you to be aware of that there are inductors that may look like resistors, but when you measure them, they may appear to be a short because the winding is really just a wire and its resistance is very low. So make sure that you know what type of component it is. Is it a resistor, or could it possibly be an inductor? And if it's an inductor, then this particular color code table would be applicable as to measuring or as to determine what the inductance is. Inductors can be measured by what we call an LCR meter. LCR meters are specifically made to measure inductance, capacitance, and resistance. And again, they're called LCR meters. And so to measure the inductance, we would just plug it into a meter such as this, and it would tell us what the inductance of that inductor is. In this next part, we find out how the inductor actually operates. What is its functionality when it receives current, when it's charging up, when it's discharging as well. One of the things that we need to be aware of is how we have an induced voltage when a conductor is cutting the lines of flux of a magnetic field. So how an inductor works can be better understood by understanding Faraday's law of electromagnetic induction. And this is how a generator produces current and voltage. In taking a look at the diagram, when you have a wire and it's being moved downwards and it's cutting those lines of flux shown by the dashed lines, which are established by the north and south fields, when we have this wire and it's moving and in a sense cutting those lines of flux, then we'll have an induced current in the conductor, in the wire, and we'll also have a voltage across the ends. Now, if the conductor did not move, say it was just staying still, it was just static in that field, if it was not moving in relation to the magnetic field, then no current and no voltage would be established. So there has to be action. So the wire has to be moving, okay, across that field in order for it to create a current or to establish a current and a voltage across it. Now, if we wanted to create a larger amount of current and a voltage that would be higher as well, we could do that by putting several turns in the wire. So therefore, this is how a generator is made, or an alternator. And so therefore, this will increase the amount of current and the voltage as well. But again, that coil would have to be moving in relation to the magnetic field. And when it does move, then current is established and a voltage as well. When an inductor is charging up, this is when it experiences induced voltage. Now, an induced effect is always such as to oppose the cause that produced it. As current is applied to the inductor, a magnetic field develops. As the magnetic field is increasing, the magnetic flux lines cut the coils of the inductor, producing a current opposite of the current supplied. When the magnetic field is fully established, the inductor acts as a short. When the supply current is removed, the magnetic field collapses and the flux lines cut the coils of the inductor, once again producing a current and a voltage, thus releasing the stored energy. In a summary of this, we could say that when the inductor starts to charge up, it starts to create an electromagnetic field around it. Again, it's going to go from having no field to having a field. So that means that the field is actually going from 0 and it's increasing to a certain point. Well, as it's per se increasing, it's in a sense growing, and that causes the coil to cut lines of flux. And so therefore, in a sense, when it's charging up, it's actually acting as a generator. But the interesting thing about it is that the energy that it's creating, especially the current, is opposing the current that's charging it up to begin with. Then, when the capacitor's energy is sent back to the circuit because there's no power there to keep it charged up anymore, then it's going to release its energy by that field collapsing down to 0. And as that field is collapsing, the lines of flux are going to be cutting the coils of the inductor, and therefore it's going to become a generator once again, releasing the energy back into the circuit. Here we have an examination of the transient phase. This is when the inductor is getting charged up, and so therefore it's going to be storing energy. As stated here, the initial condition of the inductor when the switch is closed is that of an open circuit. So therefore, when that switch closes, the instant that it closes, the inductor is still acting as an open. Once a steady state condition has been reached, meaning that the inductor is fully charged up, the inductor acts as a short. Now the inductor has a time constant, and the time constant is tau is equal to L over R. Again, the time constant tau is equal to the inductance over the resistance. So again, tau is equal to L over R. And looking at the plots on the right side, the very top one shows what is happening to the current. As what was stated in the previous slide, is that as the inductor is charging up, an electromagnetic field is being established. It's going from 0 to a certain height. And as it's changing to reach that height, it's going to send current back opposing the I sub L. So that's why the current here on this plot is going to be ramping up until it reaches its final value, where I is equal to E divided by R. And what's happening then is when the inductor charges up all the way, it acts as a short. And if it acts as a short, then the only resistance that you have there, or the only opposition to current flow, is going to be R. So then the maximum current is, again, your voltage source divided solely by the resistance, because the inductor at that point, once it's fully charged up, is acting as a short. So if we look at the second plot, this is the voltage across the inductor. As was stated earlier, when the switch is first closed, the inductor acts as an open. So therefore, it's going to have the full voltage of the voltage source, of the E value. And then as the inductor charges up and the current ramps up to a maximum amount, and then finally the inductor acts as a short, you can see that when the inductor acts as a short, the voltage across it has gone down to 0. And the final plot on the bottom shows you what's happening to the voltage across the resistor. And this is following the current. If we look at the top plot, you can see that the curve is in the same way. It is ramping up. So as the current increases, the voltage across the resistor will also increase. Here we have the equations to solve for the transient curve values, such as if you wanted to know what the current was at any point on the curve, or what the voltage across the inductor was. So the equations are set here, and in these, t is in seconds after it started to charge. Please note that for the voltage of the inductor, the longer the time from when it started charging, the less the voltage it has across it. Because once it reaches 5 tau, the voltage across the inductor is going to be 0 volts. Why? Well, because the inductor is fully charged, and when it's fully charged, it acts as a short. The current, of course, since the inductor is shorted, it's going to allow the maximum current to flow. That's why at 5 tau, the current is going to be at a maximum value. So what happens if the inductance is increased, or for example, if you change one inductor, okay, for another, but for one of greater inductance value? So as the inductance increases, it's going to take longer for that inductor to charge up. Here we have an exercise, and we're asked to determine the time constant, the total charge time, and the current through R1 once a steady state condition has been reached. And finally, we're also asked to determine the current isobel at 1/3 of the total charge time and at 2/3 of the total charge time. Well, let's first determine the time constant. We know that tau is equal to L over R. Therefore, the inductance is 4 henries, and we're going to divide that by 2 kilo ohms. And that gives us 2 milliseconds. And total charge time would be capital T, and that'd be 5 tau, which would be equal to 5 times 2 milliseconds. So therefore we get 10 milliseconds. Once steady state condition has been reached, the inductor is going to be acting as a short. So just imagine a short there. And now to figure out what the current would be, and really what your maximum current would be, I would say that I max is equal to your E divided by your R. And that would be 50 volts divided by 2 kilo ohms, and that's equal to 25 milliamps. To determine the current isobel at 1/3 of the total charge time and at 2/3 of the total charge time, we need to figure out what 1/3 of the total charge time is to begin with. So total charge time is 10 milliseconds. So therefore, 1/3 of t is equal to 10 milliseconds divided by 3, which is equal to 3.33 milliseconds. And 2/3 of the total charge time is equal to 10 milliseconds, and that's going to be multiplied times 2/3, and that's going to be equal to 6.66 milliseconds. Using the equation to solve for I, we can work out these problems now. Solving for isobel at 1/3 of the total charge time gives an equation of I is equal to the voltage, which is 50 volts, divided by the resistance, which is 2 kilo ohms, times 1 minus E to the negative and we have a resistance of 2k ohm times the time that has elapsed from when the switch was closed, which is 3.33 milliseconds, all over the inductance, which is 4 henries, and that gives us an answer of 20.3 milliamps. Now solving for I at 2/3 of t is going to be equal to 50 volts over 2 kilo ohms, 1 minus e to the negative 2 kilo ohms times 6.66 milliseconds over 4 henries, and that's equal to 24.1 milliamps. Here we have the release phase. The one thing to notice here is that the energy is going to be released back into the circuit. So once that switch is open, that current that was charging up the inductor is no longer there. So therefore, that electromagnetic field that has been established around the inductor will collapse. And when it does that, the energy that is in that field will return back to the circuit. Now please note that the way that the inductor was charged, it had a polarity of positive on top, as shown here in this diagram, had a positive on top and a negative on the bottom. When the inductor is discharging, when it's releasing its energy back, please notice that now the positive of the inductor is on the bottom side with the negative on the top side. So in other words, when it's charging and then when it discharges, its polarity will reverse. It'll switch on it. Now, how does that affect things? Well, if we look at the plots, we can see as far as what's happening to the voltage at the very top plot here. We see that the voltage across the inductor first shows that the inductor is charging up, and then the voltage as the inductor charges up finally reaches 0. Then here we see where the switch is open. When the switch is open, the energy in the inductor is going to be released back, but it's going to do so as a voltage spike. You can see that the voltage spike is very, very huge compared to what charged it up. For example, the plot here shows that the voltage source has 50 volts, but you can see that the voltage spike is shown to have a voltage of about a negative 125 volts. So that's one thing to be aware of, is that the energy of the inductor is going to be sent back to the circuit, but as a voltage spike, and that voltage will exceed the voltage that charged it up to begin with, and that it's going to return its energy in a polarity that is opposite as to how it was charged. For inductors, the average induced voltage is defined by the voltage across the inductor is equal to the inductance times the rate of change of current of the inductor over the change in time. Now this equation is more related to AC, and so with that I have a plot here. I'm going to put an AC waveform, and we'll see how the current relates to the voltage and how the voltage relates to the current, and so on and so forth. If we were to take our equation and let our inductance equal to 1, we could say that the voltage of the inductor is equal to just the change in the current of the inductor over the change in time. And then the other thing that we could do is to see this as a whole and refer to this as just the slope. So therefore we can apply that to the plot of the sine wave here. And one of the things that I want to do is to annotate where the slope is the greatest, where the slope is the smallest, and so on and so forth. So at this point, we have the slope being at a maximum, and it's a positive maximum right here. It's a positive max. At the very top, well, it's, in a sense, it's kind of like a flat line up there, right at that dot. It's flat. So therefore, your slope would be at a minimum. And then if we took it right here, the slope would be at a maximum, but the travel is downward, so it'd be a negative maximum value. And then if we took it right down here, the slope would be a minimum. Now, please don't forget that your slope is equal to your rise over your run, or in other words, it's your y over your x value. Now, continuing on, and at this point, we're at a maximum, and again, it's a positive maximum right there. Please note that this AC waveform here is referring to the current. This is your I sub L. So what will the voltage be doing? Well, the voltage is the result of your inductance times your slope. Well, if your inductance was left to be 1, as we had previously stated, then really the voltage is proportional to your slope. And if we were to look at the voltage here, where we have the plus max in orange, well, that would be that the voltage is equal to that right there. It's proportional to that, so that's going to be at a maximum. And if we were just to say that our maximum was here at that point, and then where we have the minimum, well, the minimum would be 0. We have a slope of 0, so the voltage would be 0, so that would give us a point right down here. And a negative max slope would give us the greatest amount of voltage, but in a negative fashion. Let's just put that it's going to be right there. And then for the next point, it's going to be at a minimum, and your slope is equal to 0 there, so therefore if the slope is equal to 0, the voltage is also equal to 0, so for that point we would have a voltage of 0 there. And then for the plus max again, we're going to have the maximum voltage, and it's positive. We said the maximum was going to be represented by this amount of height right there. Now, if we were to connect all these dots, what would we have? Well, if we're looking at it, we would have something like this. Now, my drawing wasn't exactly perfect, but if we were to follow it through, we could see that it's going to do something like this. So it's going to be a sine wave as well, but this is for the voltage of the inductor. Now, one of the things that is apparent right here, that the voltage and the current are not occurring at the same time. This right here is your time, that's your x-axis, so it's not occurring at the same time. So one of the things is that if the voltage and the current are not following each other in respect to time, right, that they're not occurring at the same time, then we can say that these are out of phase. So yes, the voltage and the current are out of phase by 90 degrees. So in this instance, we could say that for an inductor, that the voltage leads by 90 degrees, okay? Or we can also state it as that the current lags by 90 degrees. So there's two ways to view this, but it's really saying the exact same thing. So what is this kind of inferring, so on and so forth? Well, since the voltage here, okay, is leading, that means that the voltage can change much faster than what the current can, or it's going to change prior to what the current can. So another way that we could view this is that for an inductor, that the voltage can change instantaneously but current cannot. Now, when you have inductors in series or in parallel, we need to come up with the total amount of inductance. So placing inductors in series increases the overall inductance. So therefore, the total inductance for inductors in series is the sum of the individual inductances. So if you have L1 and you have L2 and you have L3 and they're all in series, simply just add them up. Placing inductors in parallel, though, decreases the overall inductance, and the total inductance can be obtained by using a formula similar to resistors in parallel, which would be that your L total would be 1 over L1 plus 1 over L2 plus 1 over L3, and so on and so forth. Just to make that point perfectly clear, let me show you. So let's say that we had some inductors that are in series, such as this. Now these are just air core inductors. I don't have any type of core being shown there. But from the points of A and B, and let's say that this was 0.5 henries, and let's say that this was 1 henry, and let's say this was 4 henries. Well, the total inductance, L total, would be equal to the sum of those, and that would be 5.5 henries. Now, if we had two inductors in parallel, for example, and we had something like this, we had points A and B right there, and if this was 2 henries and this was 4 henries, then L total from the perspective of points A and B would be equal to 1 over 2 henries plus 1 over 4 henries, which would be equal to 1.33 henries. So here we have two diagrams. One is showing inductors in series and the other one is showing inductors in parallel. In this diagram, we are asked to reduce the network to its simplest form. So let's take a look at it. So one of the things that we need to do right off is we need to ascertain as to what's in series, what's in parallel. That's very important. And hopefully we can see that we have a junction here and we have another junction right there. And what that does for us is that it puts L2 in parallel with L3. That's in parallel also with L4. So we have 3 inductors that are in parallel, and then all of that is in series with L1 and resistor of 1.2 k ohms. Let's figure out what the parallel equivalent is. That would be 1.2 henries in parallel with 1.2 henries in parallel with L4, which is 1.8 henries. And all of that gives us an equivalent of 450 millihenries. Now we can reduce our diagram to look something like this now. And our resistance be right here. This is 450 millihenries, and the top inductor is 560 millihenries. Now this can be reduced one more time, and that would provide us a single inductor with a single resistance. So this is going to be the simplest form. The resistance will be 1.2 k ohm, and since these two inductors are in series, we would just add them, which gives us 1.01 henries. As was stated earlier, once the inductor is charged up, it will act as a short circuit. So once steady state conditions have been reached, the inductor is acting as a short. The term steady state implies that the voltage and current levels have reached their final resting value and will no longer change unless a change is made in the applied voltage or circuit configuration. For all practical purposes, our assumption is that steady state conditions have been established after 5 time constants of the storage or release phase have passed. As seen in the bottom diagrams, once the 5 time constants have passed, the inductance of 2 henries is now viewed as a short. Here we have another example, and again, after 5 time constants have passed, or after the inductors have charged up, they act as a short. So inductor on the top, which is the 10 millihenry value, is now viewed as a short. So R1 is now shorted out. And the 6 millihenry inductor is also viewed as a short now. And so therefore, the only value of resistance in that path is just R2 then. And R2 is in parallel with R3. And that is all that the 21 volts sees, is just R2 and R3 in parallel with it. R1 is not of any concern, again, because the inductor is shorted, so therefore it's shorted R1, so all the current flows around R1, so R1 never plays a part after the inductor charges up. In this exercise, we are asked to find the current I sub L and the voltage V sub C. Once steady state conditions have been reached, we see that the capacitor is acting as an open and the inductor is acting as a short. Now the question was, what is I sub L and also what is V sub C? Well, to solve for V sub C, since current does not flow through it, we have no current flowing through there. Therefore, if we measure from this point to the other side of the resistor right there, that would still provide us our V sub C, because again, current is not flowing, so therefore the value of voltage that we have on one side of R3 is the same as that as on the other side. So therefore we can measure across here to get our V sub C. Now the other thing is that I sub L is a current flowing through R2. So therefore, in a sense, I sub L is equal to the current through R2. So therefore, we can redraw this circuit to look something perhaps like this. We have our voltage source here. That's 10 volts. Have a resistance of 2 ohms. And we have R2, which is 3 ohms. This is R2, and this is R1. So we want to know, is the current flowing through R2, because that's I sub L. And so we can state here that I sub L is equal to the current through R2. So we'll solve for that. And then also the voltage, well, the voltage across the capacitor is really the voltage across R2 as well. And so that right there can be stated as V sub C is equal to the voltage across R2. Now solving for the voltage across R2, we can use the voltage divider rule, which says that 10 volts times 3 ohms over 5 ohms will give us the voltage, and that is equal to 6 volts. Solving for the current through R2, and when you think about it, there's only one current flowing. There's only one current flowing through the entire thing here, so that really is I sub s in this instance. So therefore, what is I sub s? Well, I sub s is equal to the voltage over the resistance, which is equal to 10 volts divided by 5 ohms. That's the total resistance seen in the path. So therefore, that current comes out to 2 amps. For this exercise, we're asked to find the currents I sub 1 and I sub 2 and the voltages V1 and V2. And of course, this is once steady state conditions have been reached. Well, once steady state conditions have been reached, the inductors will act as shorts. So therefore, I will replace them with a short. There. And now the capacitors are going to be responding as opens. So to take care of that, I will just open the circuit up right here, indicating that it is an open. In analyzing this circuit, we can see that current will not flow through R2 and current will not flow through R4. So all of the current will be flowing from the voltage source and will go all the way around like this. So therefore, we can see that current I1 is equal to current I2 because it's the only current. And really, those two currents are the same as what we call I sub s. So therefore, I sub s is equal to 50 volts divided by all the resistance in that path, which is going to be R1 plus R3 plus R5, and so that is 10 ohms. So the current is equal to 5 amps. Next, let's concentrate on solving for V1 and V2. Since current is not flowing through R2, we do not have a voltage drop across R2. That means that the voltage here at this point is the same as the voltage at this point. So therefore, in a sense, V1 is the voltage from here to there. So in a sense, from that point to that point. And the same thinking applies to the other side where R4 is found. And that is, again, current is not flowing through R4, therefore it cannot have a voltage drop across it. So therefore, the voltage found here in respect to ground is the same as found over here in respect to ground. So therefore, when we're solving for V2, we're really solving for the voltage across there. And since R2 and R4 don't come into play, then we can simplify the circuit a bit, and we have a circuit that looks like this. Now V1 is the junction from here to ground. So V1 is from there to there. And then V2 is really the voltage across R5, which is 7 ohms. When you look at the circuit, though, all it is really just a series circuit. And we've done these lots of times before. So really what it comes down is really to solving the voltage divider problem for each one of these. So let's set the equations up. For V1, it's equal to 50 volts times, well, the voltage across what we're trying to solve is really the voltage at that point in respect to ground. So really it involves R2 and R5. So that's going to be 8 ohms over all of the resistances, which is 10 ohms. And that'll provide us V1. And V2 is equal to 50 volts. And the voltage V2 is just the voltage across R5, which is 7 ohms, over all of the resistances in the path, which is 10 ohms. Now solving for both of those, we have that V1 is equal to 40 volts and V2 is equal to 35 volts. Just like a capacitor, an inductor also stores energy. It does not dissipate the energy. It doesn't actually turn it into work. It doesn't use it up. It merely stores it. And here we have the power curve for an inductive element under transient conditions. So as the inductor is charging up or discharging, this is the power across the inductor. And energy stored by an inductor is given by 0.5 Li squared. So this is the energy, which is in joules, and this is the energy stored by an inductor. So all we have to know is the inductance value and the current flowing through it to figure out how much energy is stored in it. And this concludes the presentation on inductors.